Welcome to iLecture Online, and here's another example of how we work with rotational motion. Let's read the problem. It says a turntable rotates with a constant angular, it should say angular acceleration, I didn't write angular, but it should say angular acceleration of 3.5 radians per second squared. After 5 seconds, it has rotated through an angle of 50 radians. What was the initial angular velocity? All right, so let's draw a picture, try to get a mental feel of what's going on here. So we have a turntable that's rotating around. It has some initial omega, and we don't know what that is. Matter of fact, that's what it's asking for. What is the original omega? It does travel through an angle by going around and around and around for a certain amount of time. It says 5 seconds, so time equals 5 seconds. It goes through a distance, angular distance, we can say, of 50 radians. Okay, what else do they tell us? They do give us the angular acceleration. It has a constant angular acceleration of 3.5 radians per second squared. Okay, so this is given, that's what they're asking for. The best thing to do now is to look at our three equations right here and see which of those three equations is the most appropriate one to solve this problem. And sometimes it may take more than one. It may take two simultaneous equations to solve the problem. So let's see here. We have theta, we have time, we have alpha. So if I look at my first one, we have theta. Theta initial is not known, but then if we assume that we start at 0, that's a good assumption. This is what we're asking for. We're given the time, we're given alpha. It looks like this equation right here is probably the right one. We may be in luck that that's the only equation that we need. Let's try it. So we have theta is equal to theta sub naught plus omega sub naught t. This is the variable that we're looking for. Plus 1/2 alpha t squared. And assuming that we start from theta equals 0, we can do that, and this is the total distance covered, 50 radians. I think we're in business. Let's now put some numbers in there. So we have 50 radians is equal to omega initial, which is what we're looking for, times the time. The time is 5 seconds, plus 1/2 times the angular acceleration of 3.5 radians per second, times time squared, which is 5 squared. Now notice I did not put in the units because it gives us a cleaner equation to work with, and this is the variable that we're looking for. So cleaning things up a little bit, we have 50 is equal to 5 omega sub naught plus 1/2 times 3.5 times 5 squared. It's 25. Let me grab the calculator for that. So we have 25 times 3.5 divided by 2, we get 43.75. Okay, so now we have a nice linear equation we can work with. Let's solve for 5w. So I'm going to turn the equation around. So we have 5 omega sub naught is equal to, I did call it w. It kind of looks like w, but it's actually omega. So 5 omega is equal to 50. When we move the 43.75 across, that becomes a minus 43.75. So we have 5 omega sub naught is equal to 50 minus that. That gives us 6.25. So now let's move over here. So we have 5 omega sub naught equals 6.25. And of course, now we divide both sides by the coefficient in front of omega. Cancel that out. We have omega sub naught is equal to 6.25 divided by 5 equals exactly 1.25. Now, what are the units? Okay, omega is going to be in terms of radians per second, so we can write radians per second. And there's our answer. The original omega, the original angular velocity was 1.25 radians per second before the object began to accelerate at 3.5 radians per second squared. And that's how you do this problem. Not too difficult, so hopefully that will help you understand how to work with rotational motion. Let's see if I can come up with some more examples to show you how to use this. All right.